Hello, everybody. Come on in. Welcome, welcome. I'm going to give this one more minute. I'm running a minute late today. Apologies. We have a lot of people registered for the webinar, so I'm going to give this, I'll steal a minute from my housekeeping chores and I'll go through it quickly to regain that minute. Okie dokie, we have a goodly number of people here already, and I think we will kick things off. So hello, formally, and welcome, everybody. My name is Alan Barr with COEH Northern California, and on behalf of the NIOSH-supported education and research centers throughout the country, we're pleased to bring you another installment of the 2024 ERC Ergonomics webinar series, where we offer free monthly webinars on various topics on human factors and ergonomics. This collaborative effort on behalf of each of the ERC's continuing education programs aspires to provide access to current research supported through NIOSH ERC programs. Thanks again for joining us today. If you logged in via your registration email, you will get a link to an evaluation form that will qualify you for a certificate of completion worth one continuing education contact hour. You can join us next month for the next webinar in the series is on the 20th of November is Ergonomics and Your Parents, Musculoskeletal Challenges of Home Health Care for the Loved One from the Defense Centers for Public Health's Perspective. You can register for that and other upcoming webinars at coeh.berkeley.edu/webinars. That's coeh.berkeley.edu/webinars. For today's webinar, you will be muted during the presentation as usual. If you'd like to ask a question, then we do encourage you to do so. Please enter it into the online Q&A. We'll save some time at the end of the presentation to address your questions. The webinar is being recorded and will be made available along with past webinars on the COEH Northern California YouTube channel. Please take a moment to like and subscribe to that channel to help us continue to grow. Today's webinar, titled Control of Localized Fatigue, and today's presenter is Dr. Thomas J. Armstrong. Dr. Armstrong is a professor in the Department of Industrial and Operations Engineering and the Department of Biomedical Engineering at the University of Michigan. His education includes a BSc in Aerospace Engineering, an MPH in Industrial Health, and a PhD in Industrial Health, Physiology, and Engineering, all from the University of Michigan. Now retired from teaching, Tom formerly taught undergraduate and graduate engineering courses in work analysis and design and work-related musculoskeletal disorders. He continues to do research concerned with the analysis and design of work methods and equipment. He's also a certified industrial hygienist, a certified professional ergonomist, and a licensed commercial pilot, and a certified flight instructor. It's so fantastic. With that, we appreciate your time today, Dr. Armstrong. I'll hand the floor over to you.
Okay, well, thank you very much, Alan. It's a pleasure to be here today. And I might just say a little bit about myself. Thank you for your kind introduction. I've been really looking at issues related to local musculoskeletal disorder, and actually started out looking at fatigue since I did my graduate work back in the 70s. So it's interesting because I started out, my original dissertation work was looking at a model for localized fatigue during sustained static exertions of the hand. And then we kind of got going on things like carpal tunnel syndrome, tendonitis, and did lots of epidemiology and laboratory kinds of studies. And now I find myself kind of coming back to the localized fatigue problem issues, which, in some ways are much less intractable than some of the more complex issues that we've spent so much time on over the years. So it's really a pleasure to talk to you about this today. I do have a slide deck, and you're welcome to follow along, and I'll try to make some of the links available. There is a link to the slide on the cover or on the front page here. The first slide is basically some links to some online resources, and one of the things I'm doing as I've kind of moved into retirement is trying to develop some web tools that sort of summarize what we've learned about musculoskeletal disorders and put it into a form that people can use. And these are just some examples. You can go directly to the links by clicking on them, or you can take pictures of the QR codes and look them up, get to them that way. And I'll be referring to some of these as we go through our discussion today. The one that we'll spend the most time on is this one in the upper left corner. It says management of localized fatigue. And this is a fairly long web page. I think it goes beyond being a web page. I think it's becoming more of a web book, or at least a web chapter. It deals with some of the issues, and the presentation today is really going to follow the outline of that. I'll draw some of the resources from it as well as we go. But there's another one when we talk about localized fatigue, we talk about workloads, and you'll quickly see that when we talk about workloads, we tend to normalize these loads based upon individual capacities. I'll get into that in just a few minutes, but it requires us to have information or knowledge of what the strength of the worker or the population is that we're concerned with. So the second resource here will give you some resources for assessing strength requirements, strength capacities, and some literature that you can go to find out what's been published on the subject and hopefully save you some time. The third one is really takes you to a page for doing some reach analysis. It's a very simple kind of model that you can play with in your own. The next two, we'll get into this a little bit today, are some web-based apps that you can use for video analysis of various work activities. And we'll actually, hopefully there'll be time where we can get into this a little bit, because one of the things that's important when we study work and try to understand stresses, whether we're talking about localized fatigue or exposure to other physical or chemical hazards in the workplace, we really have to know kind of what people are doing and what it is about what they're doing that exposes them to these stressors that may adversely affect their health. And the last ones, I forgot to put a label on that. That's just a link to my personal web page, which has links to a lot of other stuff, which some of you'll find is kind of dated and some of it's more up to date. But you can kind of thrash through it. Think of it like a garage sale. So moving on, let's talk about localized fatigue, and let's take a look backwards. Certainly, this is not a new kind of problem. And one of my favorite examples, actually comes from the Bible. It's in Genesis 2:3. In the beginning, so God blessed the seventh day and made it holy, because on it he rested from all his work that he had done in creation. So I like to point out when I talk to workers and to supervisors that even God has to have a day of rest. And if you're done work and fatigue and other kinds of handwork, you probably know that in industry they talk about rest allowances. I like to call them recovery allowances, because rest has sort of a little bit of a negative connotation when you tell employer the worker needs more rest. So I like to say they need more recovery time. There are other ways to do that besides just resting. But anyway, going back to God in the beginning, basically the rest allowance that he needed was 1/7, which is about 14%, I think, as an allowance. Jumping ahead quite a few years, the Romans were very sensitive to this issue, and there's a link here talks about how the Romans would, when they would lay siege on areas they were trying to conquer, how they would actually group their legionnaires, and they would approach in groups, and they would fight at the front, and then when they got tired, they would back up, and another group would come forward to take on the battle, and they'd be well rested. it just emphasizes how people recognize that people are more productive when they're rested. And in the case of war, that's really important. And I know I'm talking to some people with backgrounds or interest in occupational health, and I'm sure you're all familiar with Ramazzini. And Ramazzini, wrote a long time ago in his famous book, The Diseases of Workers, about how various and manifold is the harvest of diseases that workers reap from the crafts and trades they pursue. And he went on to talk about various irregular motions in a natural posture of the body that could create problems. But he also talked about, writers and scribes. And he said the diseases of persons incident to this craft arise from three causes. First, constant sitting. Second, perpetual motion of the hand in the same manner. And thirdly, attention and application of the mind. Constant writing considerably fatigues the hand and whole arm on account of continual almost tense tension of the muscle. And again, this is really what we're still studying today is, what are the limits for that kind of activity? Some of you have heard of Frederick Taylor. Taylor's always had kind of a negative connotation, I think, in occupational health settings. He's kind of known as a guy who created, really, I shouldn't say created, but he really took standardized work and structured work to a new level. But one of the things Taylor did was he actually spent some time trying to get an idea of how much people could do before they became fatigued. And he wrote about, trying to manage fatigue. And then Frank Gilbert picked this up a little bit later with his wife, Lillian. But basically, he did studies in a laboratory where he had people come in with a shovel, different size shovels, and demonstrate how much they were comfortable shoveling with different size shovels. So he could kind of determine what's an optimal combination of shovel size and density of the material they were shoveling. And interesting enough, this isn't terribly different what we've been started doing here in the 60s to study psychophysical limits of work. And some of you are familiar with the work that was done at Liberty Mutual by Stover Snook starting in the 60s. And that is really, kind of mirroring what Taylor did. Although Taylor was more focused on the productivity aspect of it than on the health aspect of it, but it's basically the same underlying concept. And then I like this one, Henny Youngman, some of you may be familiar with, as a comedian now deceased, but he one time was quoted as saying, the patient says to the doctor, "It hurts when I do this." And the doctor says, "Don't do that." Okay. Well, that's kind of what we're dealing with fatigue. It hurts when I do this, but, I'd like to say don't do that. But if your job requires you to do that, then it's hard not to do it. And then the last thing, there's a lot of emphasis on AI now, and a lot of concerns about how it'll affect people. But I'm happy to tell you, I collaborated with ChatGPT to develop a kind of a summary of what people are dealing with, and it because one of the reasons why we're concerned with fatigue is that people have to come home and often do other activities, especially females that are working in the workplace that may be taking care of kids. But anyway, I was impressed with the sensitivity of ChatGPT to these issues and ability to articulate the issues. So he wrote, "As the whistle blows, I leave the grind, hands worn and weary, feeling fatigue intertwined. The factory's clatter fades from my ears, but home awaits and the weight reappears. Shoulders aches, but there's still work to do, dinner to prepare, the laundry to pursue. I shake off the dust, trade machines for my cares in the daily dance. Love's burden always bears. Yet as I chop, I find solace in routine, a moment of peace in chaos unseen. For in every stir and every dish that I make, I weave love into meals, my heart in each cake. So I carry the weight, both seen and unseen, in the warmth of our home. I'm never alone." So anyway, I think that's, very, very nice description of what a lot of people are dealing with in the workplace today. So I think everybody has an idea what fatigue is. We've all experienced it in one form or another in different parts of our body. It's, whether it's running for a bus or whether it's just holding your computer or your iPad up so you can see it and work on it. I guess as a formal definition, I would say characterize it as transient physiological and biomechanical changes which may adversely affect. I'm sorry, I've got pictures covering up my my notes. Adversely affect motor performance and produce discomfort that results from repeated and sustained exertions of the body. I think one of the key parts of this is transient physiological and biomechanical changes. I'm sure many of you have dealt with some of the chronic musculoskeletal disorders in the workplace, but those are issues that often last well beyond the day and the evening, but become chronic conditions and can result in long-term disability. In most of the cases with localized fatigue, we're talking about something that develops and recovers within periods of seconds, minutes, or hours. And the symptoms generally should not persist from one day to the next. And if they do, that often indicates that there's something more serious wrong than the fatigue from an honest day of work. And those people should be referred to see a healthcare provider to make sure there's not an underlying pathology that merits concern. One of the things about localized fatigue, people are often kind of conditioned to try to work through the discomfort. And that's, and I think we often do this ourselves. When you're working in the yard or around the house, and you have some pain, say, well, if I can just get this done, then I'll relax. And that is interesting from two standpoints. One is that we do often try to push ourselves through these things, but also when you're working at home, you can kind of push yourself through something, but then you're done with it. In the workplace, if you try to push yourself through it, it just keeps going, until the whistle blows at 5 o'clock or whenever your shift ends. So we really have to kind of think about what are the reasonable limits, and that's one of the things we'll be talking about today. Or what are the reasonable limits to repetitive work? I do think it's important to recognize that localized fatigue may be a precursor or harbinger to serious chronic musculoskeletal disorders. And the good news is that I think there's general consensus that if we can manage localized fatigue and prevent this ongoing pain, that we can prevent a lot of the other serious tendon and nerve problems that people experience in the workplace. I can tell you there's a vast body of literature on muscle fatigue and fatigue in general. And this picture on the left here is actually a picture I put on my doctoral dissertation in the cover when it was published in 1976. And basically, I wanted to emphasize the relationship between what people were doing with their hand, the loads in the hand, the loads in the muscles in the forearm, and also in the cardiovascular system, the ability of the body to deliver nutrients to the working muscles and to help eliminate the metabolic byproducts and waste that are necessary for sustaining work. In 1993, a group of us from different parts of the world, Scandinavia and Europe, actually put together a paper, that we generally refer to as a model for musculoskeletal disorders. And the motivation for this is that we came from different parts of the world, and some people were talking about localized fatigue, and some people were talking about tendonitis, and some people were talking about carpal tunnel syndrome, and various disorders. And we really wanted to show that how these all have a common link, and it's a little bit like, the dog in the box, and one person reaches in and says, I feel something fuzzy, and somebody reaches in and says, oh, I feel something that's cold and wet, and somebody else says, I feel something sharp. And, we're all kind of looking into this box and feeling for different parts of it. And, again, I don't want to go into the details here, but I can only tell you that, we're dealing with a number of factors that can contribute to localized fatigue, and are important tools for understanding it, for evaluating symptoms of localized fatigue, and ultimately in managing it. When we talk about fatigue, and let me just back up a second, because when we look at these slides, we can quickly get into a lot of biochemistry and physiology. And, in studies of fatigue, people, have done a lot of work where they stick needles into muscles to, look at how the muscle changes biochemically during exercise, how it changes histologically over time. They've looked at blood chemistry by taking probes and needles like that. They've looked at electrical conduction of the muscle in different ways. And these are all ways that you can, try to quantify fatigue. But a lot of those aren't really useful in the workplace. It's pretty hard to go start sticking needles in people and taking samples of their muscle or getting blood draws, and then let alone having to deal with the issue of analyzing it. The most widely used survey tool for fatigue or localized fatigue is just looking at symptoms, or what we call symptom surveys. And probably one of the pioneers of this was Nigel Corlett, who published a paper back in the mid 70s. And actually, this diagram on the left was taken from his paper. But basically, he would show people a picture of the body and ask them to color in areas of discomfort. And he'd often try to, quantify these at least on a ordinal scale by saying, are there any areas where you experience discomfort? And they maybe indicate yes. And he's okay, show me the area where you experience the most discomfort. And then show me the area where you maybe feel the next more level extreme. It's able to show a correspondence between, the spatial distribution of the symptoms and the biomechanical loads on the body as people were doing these tasks. We can often take this a step further in quantifying it by showing them a picture of the body and then putting, either visual analog scales or numerical scales next to each part. So when they say, well, are you experiencing discomfort? And they say, yes, well, show me where it is, and then give me an idea how much discomfort you're experiencing on a scale of 0 to 10. And if you've ever been in the doctor's office now, it seems like they all have charts on the wall now of, tell me about your pain, and they have smiley faces next to it, or going from smiley faces to frowny faces. But these are effective ways of, getting an idea of what kind of discomfort. Recognize that when we do these surveys, that these symptoms will vary from worker to worker, and they'll also vary over the course of the day. So if we're going to do these kind of surveys, it's important to make sure that you catch people in the morning, beginning part of their shift, maybe midway through it and toward the end of the day, so you can see what kind of progression you get in symptoms. Don't be surprised if people come to work in the morning with some symptoms, and whether it's the ongoing condition, whether it's because they slept in their shoulder last night, or because they were doing some kind of other physical activity. And, so again, it's important to kind of look at how things change from the beginning of the day to the ending or end of the day, and also get an idea how much it might vary from person to person. This chart on the right just shows how we might track discomfort over time. And this is actually from the web page I referred you to earlier, and you can kind of go and play with this. So it's really set up to do an in-class exercise where we can ask people to kind of click on these dots at different points while they're performing a task. And a task I often use, which is actually pretty realistic, but also it's one we can do in a classroom, is just simply asking people to hold an iPad out in front of them. And, and this is a pretty common activity. You see a lot of people, holding an iPad and doing something with it with the other hand. So that works well. And what you'll see is that these symptoms just kind of keep etching up, and, you can kind of focus on different parts of the body. Usually we focus on the shoulder because, just the weight of the arm holding it up in front of you will generate significant discomfort over time. Okay, well, it's, maybe enough said about that. Let's talk a little bit about different kinds of work. I like to, we really put work and fatigue into two bins. And again, both cases, we're talking about localized fatigue, and localized fatigue being distinguished from whole body fatigue, where, like you're running after the bus or you're trying to run a marathon and, your heart's beating fast and you're exercising all parts of your body. Here's a good example of carrying a toolbox or carrying a suitcase. And, I've used this example for many years. And, I used to travel a lot, visiting factories in different parts of the country. And I can tell you, if you were traveling on an airplane 40 years ago, a commercial flight, you we didn't have roller bags in those days. Like, people were carrying suitcases, and you saw a lot of people running to the airplane carrying their suitcase. So we used to make case studies out of this. How far can you carry that suitcase? Or now it's more like you're going to be carrying a toolbox because everybody's using roller bags. But anyway, this gives you an idea what the biomechanical load pattern would be for a task like this. I've basically got a timeline here, and I've got a kind of a scale for several different factors we're considering. One is the weight of the toolbox, which I've plugged in here is 40 pounds. And we've got a weight, or we've got a rested grip strength of the worker. And we use for our fatigue calculations, we actually calculate the ratio of the load weight divided by the strength for that particular kind of activity. And I'll say a little bit more about that in a minute, because it's very important that when we do these calculations of relative workload, that we use the strength based on a same kind of posture that the task is performed in. So in this case, we've got grip strength, or what we call a hook grip, which is approximated by a grip, or what we call power grip position. And we calculate the workload as percent of maximum voluntary contraction, or percent MVC. And you'll hear people use this term all the time when they talk about fatigue, and also other disorders involving musculoskeletal issues. But anyway, we calculate the ratio here, and I used a load here of 40 pounds and a strength of 100 pounds. And I just noticed I got 40 divided by 100 equals 50. Excuse me, that was, I made some edits on these slides and didn't change everything. So that would be 40 pounds. Percent MVC. And I also see here that I've got sorry. I'll tell you what, let me because I looked at the chart here, you can see, well, we've got a percent MVC here of over 60 pounds. So this slide is morphed from several different situations. I'll put in the 40 here. And what we would end up with here, just to carry this through, is let's come over here. I'm going to write this out. Percent MVC would be equal to 40 pounds of the bag divided by 100. And you can see I chose this because it makes the division really easily for an old man. And we'd get a 40% MVC. Okay, so that's basically how we would characterize the workload on the hand. Now, you could do the same thing for other parts of the body, but now one of the things that makes this interesting is because in terms of the muscle load, it's really greatest on the hand. When your shoulder's at the side of your body, your your arm is really exposed to traction forces, which tend to stretch it, and it doesn't really require active joint rotation. So even though there can be significant biomechanical loads, and if we had more time, we'd go into elaborate discussion of that. But for practice purposes, the major issue or major limitation, at least in short term, is going to be the ability of the hand to sustain these grip forces. So we'd end up with a percent MVC of 40%. And when I did this originally, I think this was set up for female strength, which was much less, and it gave a percent MVC of what do we have there? About 70% MVC. Anyway, let's just kind of jump ahead here. And there have been a number of studies, and let me go back to presentation view here, or slideshow mode. I get confused between Google Slides and PowerPoint. One's its presentation view and the other is slideshow view, and then I start looking for the name. It's not there. Okay, so the slide on the left is actually from my dissertation work many years ago, published in '77. And what we did here is we actually asked people to exert a force. Well, first we measured how strong they were. And we'd use a device, something like this. This is a grip dynamometer. And these are readily available. I think I paid $30 for this one on Amazon. This used to be a $500 medical appliance that you bought from Medical Supply House. So these things are readily available now. So if you're doing a lot of studies on this, it's a great demonstration tool, but also it's a useful tool for getting an idea of the strength of the people that you're working on or working with, hopefully working with, not on. But anyway, and then what we do is we'd ask them to hold some fraction of that strength as long as they could. And as they did that, we'd ask them to indicate when they started to experience any objectionable discomfort. And by objectionable, we meant discomfort that might cause them to um, pause, to set something down and take just a micro break or something. When you're carrying something, sometimes you set it down. It makes things a little easier. So anyway, and we asked them where they experienced discomfort in their hand, where they experienced objectionable discomfort in their arm, which is where all the muscles are supporting the hand. And then we saw how long we had to maintain that to the point where they absolutely could not sustain the exertion. And you can see that people experience objectionable discomfort long before they reach the point of exhaustion. And there's an important lesson here because we have different criteria for different kinds of tasks. If you're trying to catch an airplane or catch a bus and you're carrying your bag, you're probably going to carry that bag to the point of exhaustion, and then you're going to switch it to the other hand, unless you got two bags, one in each hand, and then you're really stuck. But anyway, in that situation, we might be considered with maximum exhaustion. Or if you got two people carrying a stretcher, in an emergency situation, we're concerned with how long they can maintain it before they reach exhaustion. But if we got people doing everyday tasks, or somebody carrying their toolbox from one workstation to the next, or holding a tool, then we're probably going to be much more concerned with limits here based on the time to objectionable discomfort. And if you go to the web page I referred to earlier in fatigue, you'll find that there's this graphic will be there, but also there's some active scripts. So if you type in your value here for fatigue, and here I got 50% typed in, you can see this tells us that we'd have a time to exhaustion of 113 seconds, which is shy of 2 minutes. But people begin to experience objectionable hand discomfort, like at 36 seconds, or objectionable forearm pain at 60 seconds, or close to a minute. So again, you can see that there's a substantial difference between the time that this becomes uncomfortable to the time it becomes really undoable. There was another study done by Linda Frey Law. It was actually a meta study. Since 1977, there were only a handful of studies where people had done these kind of things, but since then there's been innumerable repetitions of this kind of work, and for different parts of the body. And Freylaw and Avon actually compiled this data in a meta kind of study and developed general equations where they pooled the data and showed the discomfort for different body parts. And you can see some parts of the body actually have longer endurance capacities than others. And they weren't looking at time to discomfort. This was just time to exhaustion. And there's probably differences in those criteria for exhaustion, but this gives you an idea of kind of what these curves look like and how it would vary from one part of the body to the next. You can see the ankle, it really has a long time to exhaustion. The trunk is very high. The elbows is pretty high. The hand is kind of in the middle, maybe depending upon which part of the curve. These are very nonlinear curves, you can tell. They're kind of exponential type equations. And people spent years, or hours putting different kind of models to these things. That happened to my slide. Do I have a missing slide? I guess I do. I have a blank slide. Sorry about that. Anyway, again, we need to have hand strength data to make these work. We can either measure it for the individual that we're concerned with, or you can go and do your own survey, although that's pretty time consuming because it's not completely trivial when you do this, because you can see there's things like just spacing of the handle that become important, how rested people are when they're tested. So if you go survey workers at the beginning of the shift versus the middle of the shift versus the end of the shift, you're probably going to get different data. There are a few studies though where they've done fairly large populations and the conditions have been very closely controlled. And one that we cite a lot is by Mathiowicz, which was actually done in shopping centers in Milwaukee, Wisconsin. And they did a number of different postures of the hand. But I just want to kind of emphasize here the differences from one population next. And these tables, and you can find these if you go to that link I gave you on the the strengths. So if you go to those links at the beginning of the page, there's one called strength demands and capacities, and you'll find these tables in there. And you'll also find links to the original references if you want those. But let's just look at grip as an example here. You can see that right hand, usually the right hand is the dominant hand 9 times out of 10. Strength, ranges from, really a maximum here in the 20s and 30s, and then decreases down here to 90 by the time you're approaching 70. You'll also see that the right hand or the dominant hand in most cases is about 10+% greater than the non-dominant hand. You can see that the standard deviations go with this are fairly high. The standard deviation tends to be somewhere around 17 or 18% of the population, increasing with age. You'll see there's a substantial difference between males and females. Typical female strength is about 60% of the male population, and so on and so forth. So when you're doing designing tasks where you're concerned with fatigue, you really do need to think about the population that's going to do this. And it gets kind of tricky because you can see that if you're designing this for young people, you're going to design for people who have a capacity of 120 pounds. If you're designing this for older populations, you're going to design this for people with a capacity of 90 pounds. So what do you do if you're designing something, for consumers to use? Do you design for the young people or design for the old people? Or what about manufacturing? Now, the good news is this is a cross-sectional study of the population. If you look at strength for workers, people are constantly using their hands, you'll find that the strength is fairly constant up until about age 60, where people start to drop out of the workforce, and then the force tends to fall off. So, the old saying, use it or lose it, is important. The other point I want to emphasize is there's a big difference here between grip strength and pinch strength. You can see down here the pinch strength, we've got well, I guess I made a mistake on this slide too, because I got both slides here for grip strength. I'll fix that in the slides that get posted. But you'll find that the pinch strength here that we're looking at is typically about 15 to 20% of what we see up here for the grip strength. And the same trends occur in terms of age and hand dominance and gender. Okay, so typical problem. How far can you carry a suitcase? And, we'll assume we got a 40-pound suitcase and we've got a grip strength here of 60 pounds. I hope this is going to work for us. And we've got a normal walking pace, 3 miles an hour is considered normal walking pace. There've been studies all over the world, and people seem to really be able to consistently walk at 4.4 feet per second, which I think is about 3.1 meters, or 1.4 meters or something like that, if my memory serves me right. So anyway, how far can somebody carry this? And again, there's a link here to the page, but let me see if, I guess I'll have to go to the web page to do this. So let's see, we've got, what did I say, 40-pound suitcase, and we got 60-pound strength. So that's going to be a percent MVC of, well, just escape here a second. I'll come back up here and we'll just, so let's come down here, and percent MVC. C will be equal to 40 pounds divided by 60-pound strength times 100. And that should be equal to what, about 66.67. Okay, let's take our 66. I'm going to go to the web page here for a second, at least to show you where it is. And this is what it looks like if you open it. There's a little index on the cover. If you open the menu, we'll go down here to fatigues, sustained static exertions. And you'll see the plots I just told you about. So we said we got 66 pounds of strength here, or percent MVC exertion. I'll put in 66. No, I hope we didn't know. Let's see, close. 6. Okay. Click return. And it tells us that we would have an endurance or some of the female strength would have a endurance of about 61 seconds or about 1 minute. They'd begin to experience discomfort in 20 seconds in their hand and probably about 30 seconds in their arm. Okay. And you can come down here and you can plug in the same data for the Frey law data. And if you do that, let's go chug. Okay, well, there must be a glitch in that one. Other thing I have to fix. I made some updates in anticipation of this meeting, and sometimes they don't always go quite the way I want. So anyway, we're looking about a minute of time. And of course, the solution to this would be to get a roller bag, or at least a shoulder bag. So let's now talk about repetitive intermittent work, which is probably more common in industrial settings. So let's go to back to view slideshow. Close up a little bit. Okay. So here's an example that we'll talk about as we kind of go through this. But basically, we talk about repetitive intermittent work. We're talking about alternating periods of work and rest. Contrary to carrying that suitcase to the point where you reach exhaustion, in this case, we're going to, we do something, we put it down. And you can see here, well, let me just go ahead and take you through the example here. And then we'll talk a little bit about the limits here we're concerned with. And in your handout, it goes into talking about some of the metrics we use for characterizing repetitive work. And the metrics that you're going to be most concerned about here are the percent MVC, but we take the average value during the time in which the force is greater than the force threshold for fatigue. And there's a little bit of debate about what is that actual force threshold, but I can tell you it's somewhere between 5 and 10%. And it's not to say that people can't measure biochemical changes in muscles at lower percentages, but as a practical matter, one, it's really hard to measure percent MVCs in those ranges. And two, most jobs, people do have some flexibility and ability to move around a little bit. So it's not necessarily clear that they'd be exposed to continuous exertion. And there's a lot of people that believe that, there really isn't significant fatigue below 10 or even 15%. So anyway, we talked about the percent MVC work versus the average time. Keep in mind that these times have to be time-weighted averages. You can't just take the overall average. Means you can't just add up the numbers and divide by n. And if those of you who have backgrounds in industrial hygiene, of course, are familiar with this concept in terms of applying TLVs. Let's see. Then we talk about duty cycles, and duty cycles, the time in which the force is greater than that threshold divided by the total work time. So let's look at an example here. This is one I use a lot. This is one that it's grab my props here. I use this one because it's very easy to simulate, and it's also characteristic of a lot of things we see people doing in the workplace. But in this example, what we do is we have a job where somebody's taking 3x5 cards, and if you want to demonstrate this, is very easy because you can go to Staples or whatever those places are, these office places, and buy a bundle of cards. And basically we take these clips, and these are basically, spring clips. And the idea is you pick up a bundle of cards, one with your left hand, one cards with your left hand, the clip to your right hand, and you move the clip to the card, and then you have to open it. And there's really a fair amount of force to open this. And if you go to the link here, where it says example on your slide, sorry, I'm pointing at the screen, which you can't see. I'll move with the mouse here. You go to this link, it actually takes you through an example of kind of a detailed analysis of this and how we measure the force on these clips and compare them with the strength. And it turns out for average female, would probably require about 50% of her strength to exert this force with their fingers. So it's a fairly demanding task. Anyway, put the clip on, position an exact location. That's an important characteristic of the job, because if you just put the clip anywhere, you can do it faster than if you actually have to position in an exact location. And that affects how long that force has to be sustained. And then they set the clip aside, the paper and clip aside, and repeat the process. Okay, so here's a description of the steps that we go through to perform this job. And you can see we've got each of the steps recorded here. We've got the time at which it occurs. And this is actually a analysis of 4 cycles of putting clips on cards. And, you know, how many cycles you do really depends upon how much variation there is in the operation and actually how you're determining these times. And I don't have time to go into a lot of detail on this today, but, you know, this is pretty typical. Here's a plot of the forces. These forces were estimated to be 50% based on our experience with this. And as I've mentioned, doing about, you know, of physical measurements of the clips and of the percent of the strengths of the female population might be doing it. So you can see there's a little bit of force when they transfer the clip to the into position of the card, and then the force goes up to 50% while I have to hold the clip open and position it. And then there's a little more force than just picking up the clip to set the card and clip aside. And then there's a period of recovery while the worker is reaching for the next card. Moving on down the line, we see something like, it's just the same thing again. So let me jump ahead here a couple more slides. So this is the pattern that we see. And what we're going to do is we're going to go through and calculate the work time, the time in which the force is greater than the force threshold. I told you I'm using a force threshold here of 5%. And I'll calculate the average force during that time and the work time, and then also calculate then the recovery time, which would be when they're reaching for the clip and when they're moving the clip into position, but before they start to open it. And if we calculate those statistics, we end up with something like this. We get, this is for 4 cycles, 17.6 seconds to get the car, total time, 8.2 seconds when the force is greater than the force threshold. That gives us duty cycle total time divided by the work time of 46% and percent MVC for work of 26%. So how much is too much? Well, a few years ago, I had the honor of working with a distinguished group from the American Conference of Governmental Industrial Hygienists, Physical Agents Committee, and we put together a TLV for localized fatigue. And the rationale for this is that, 1, it's an important problem in its own right, but 2, again, it's a harbinger or maybe a precursor of more serious chronic musculoskeletal disorders. And I think it's much more manageable than some of the other issues are, and quite honestly, less contentious in many situations. I'm not going to go into great detail of this, but I'll just tell you that the TLV looks something like this, where it gives us a graphic, and there's an equation for this if you want, but it gives you a graphic of percent MVC and percent duty cycles that are acceptable. And of course, as the percent as the duty cycle increases, the acceptable percent MVC decreases, or as the percent MVC increases, the acceptable duty cycle decreases. So moving down here, we can actually compute this. Here's our plot based on our analysis of putting the clips on the cards. Shows the summary of this characterizes periods of alternating work and rest. And here's the corresponding plots. So this, if we take the observed duty cycle, which is 31%, we can come up here to our graphic here, and we've got duty cycle, let's see, duty cycles on the horizontal axis. So if we come in here at 31%, that tells us that the acceptable MVC would be like 22%, but in fact the duty cycle is 50% way up here, so we're really off the chart here. And if we come down here and put in our acceptable or put in our observed MVC, which is 50, it tells us the acceptable duty cycle would be 5%, which is very low. So both, whichever way you slice or dice this is really unacceptable, or would be physically demanding if you're doing this on a regular basis. Then we can get into discussion what we can do about it. Based upon the relationship between T rest and T work, we can actually calculate how much additional recovery time would be required. And again, if you go to the web page, it's got some web apps built into it, or some scripts they'll allow you to enter these values and determine how much recovery time. But basically, you need a total recovery time of 73.9 seconds to get this uh, duty cycle within acceptable limits for this, which is really high. Alternatively, we could consider putting, trying to find ways to reduce the force. We've had a lot of discussions with these my students in classes in the past. And we've talked about getting different clips and longer clips. When you start messing with product, it gets quite expensive. So the solution we come up with that seems to work the best is a device like this. Let's see if I can get into focus here. And I'm guessing there's at least one or two people watching that can guess what this is. If you're a mechanic, you probably recognize an arbor press as something along these lines. But this happens to be a capper for bottling beer. So when you put the bottle here, you push this down, and it gives you a lot of mechanical leverage to push that on. And we actually have a little fixture that we can put under here, use this to collapse this. And it will increase the time just a little bit to perform the task. But if you're careful with how you design the fixtures and so forth, it's not that much, certainly not compared to, the kind of change in rest allowance that would be necessary if we tried to address this through the duty cycle. Okay, so I think this is a good place to stop. I've got a couple apps that are used for doing the posture analysis, and I'll give you the links to these. One of them is a beta and still kind of the beta stage. There's a couple of glitches in it, but you're welcome to play with these, and hopefully these will be coming up to steam a little bit more better in the future. So at that point, I guess I thank you for your attention. I think I'm crowding into our question and answer time just a little bit. So
No, you're fine, Tom. Thank you. That was excellent. Very informative. If you want to take a quick peek at the Q&A box while I just pass on a couple of thoughts from audience members, you can preview the Q&A for yourself and decide where you'd like to tackle those. We only have a few things. Most of these are sort of commentary. I just want to start by saying Asa Carmona was a student of yours at U of M and is now a certified industrial hygienist. So, hey,
good.
That's good stuff.
Yeah.
Thanks, Asa. Somebody pointed out that the body map, use of a body map, and their experience showing front and back to raters is beneficial, and I totally agree with that. That's been my experience as well.
Yeah, that's really that's the most widely used and accessible tool we have for assessing fatigue patterns. I mean, there's instrumentation. We can do electromyography on people, and we can study electrical patterns and stuff like that. But for the money, I think discomfort patterns. Sure. The major limitation of discomfort patterns is that sometimes you only have one worker doing the job. So discomfort patterns work best when you got a population and you can kind of get an idea how much this varies from person to person. But you work with what you have. I'm sorry, I'm digging here for, there's Q&As. Okay. Maybe I got to stop sharing my screen.
Are you seeing that at the?
Yeah. Okay, I found
Good.
a box of question answers. Okay, I'll just go down the list, and if somebody thinks it has something that's really should be a priority, give me a shout out, I guess. But first one says, one of the biggest challenges I face in the workplace is late reporting of discomfort. I think it may be challenging for us to recognize fatigue at the early stage phases, and we wait until symptoms become severe and more impactful. And I think that's true. And again, worker education is important. To encourage people to indicate if they're experiencing any difficulties with the work, and doing some random samples periodically. Or then you have your really random samples, because when you walk through the workplace, you'll see jobs where people are reaching over something like this all day, or a large percentage of their shift, and you got a pretty good idea that they're going to be experiencing shoulder pains without doing a detailed biomechanical analysis. So do those walkthroughs and look for places where it looks like, people are either in postures that are resulting in significant biomechanical loads, or where they're lifting or handling something heavy, with their tool or with their hands. Next
I'll
one is
just I'll just paraphrase that next one for you. It's somebody's just really concerned about the fatigue, tiredness, and sleepiness terms, and the commingling of those or cross-referencing of those. When you're presenting more of a clinical definition of fatigue.
Yeah.
I'm not sure there's a question there as much as asking, seeking your opinion on the interchangeability of these terms.
No, I will confess that I'm kind of sloppy with the language here, and there's there's a lot of sloppiness in the literature in general. At the end of the day, it's your arm hurts, your hand hurts, and do you want to, how do you want to label that? So, but I agree, and that's why I kind of started out with a definition. Then I went downhill in terms of sloppiness from there. So I apologize, but I agree. That's one of the things I said. Is I like to talk about recovery rather than rest, especially when talking to supervisors. Let's see, which one are we doing next here? Besides gripping and pinching, are there any resources about hand wrist twisting? Oh yeah, there's just an abundance of literature, and in the interest of time and bandwidth, I really only focused on, the hand here. The TLV for localized fatigue applies to the hand, it applies to the elbow, and it applies to the shoulder. So, all those joints can be loaded in different ways, and there is strength data. Sometimes you'll have to dig for it a little bit, but if you just go to Google, you can find lots of literature on this. Next one says, sorry.
I was asking if your video analysis app is free to try.
Yeah, it's completely free. There's
Perhaps the
I'm sorry.
user clicked on the wrong link, but they were prompted to enter U of M username and password via that link. So I'm not sure what.
No, that maybe I got the link screwed up. Hold on a second. Now I will check it again. So there's two apps there. I'll tell you what. If you go to if I'm going to put a link in the chat here. Find the chat. See if this link works for you. And if you go about halfway down the page, you'll find links to some of these resources, and one will be the video app. And I'll add, there's a second one that goes with that now. It actually allows you to do the calculate the metrics for repetitive work. If there's interest, we could do a separate webinar sometime on just going through using the app and analyzing some sample jobs, some simple ones.
I think your contact information is available in your slide deck if anyone is interested in reaching out. You can get a copy of the slide deck from us, COEHCE at berkeley.edu as a PDF. But okay. Also I shared a link earlier from the first question. Hopefully people saw it, a link to the current slide deck, which is probably going to be edited for any ChatGPT errors. We have in fact run out of time, and I just want to say thank you very much for taking your time today. It was an excellent presentation, and I know it could have gone on for another hour. There's a lot more to talk about here. But in the time we had, it was fantastic. So just as a reminder for everybody who logged in with your registration email, look for a link for an evaluation form, and it'll qualify you for a certificate of completion worth 1 continuing education contact hour. If you have any questions for us in general, you can reach out to coehce@berkeley.edu. Okay, that's coehce@berkeley.edu. And we'll be happy to share a slide deck with you or answer any questions that you didn't get answered here today. Thank you so much for your time, Dr. Armstrong.
Yeah, it was fun.
We'll do it again.
Okay.
Bye all.
Yeah, bye-bye.